All right, our last example we will ever do this entire semester together. Example number 2, and again we're dealing with correlation and linear regression. We have two variables here. We have an emergency service that sends out emergency trucks, I guess, tow trucks, whatever it might be, and outdoor temperature. Now, notice this time we didn't label the columns in terms of X and Y. So I want to keep in mind, I would like you to keep in mind that if this does prove out to be linear, the equation is going to be y equals mx plus b. I want to take you back to example number 1. We used a person's absences to predict their grade. We used x to predict y. Well, so if you look at this scenario, if you were the manager of that emergency service, what would be the more typical scenario? Use the emergency calls to predict the temperature, or use the temperature to predict the emergency calls? Well, I can't ask you, what did you think? Yes, I agree with you. I think that you would put a number in for temperature and use it to predict how many emergency calls to expect. So you notice this time the columns are backwards from what we're used to. Y depends on X, we use X to predict Y, that kind of thing. Now, honestly, I'm not so sure that I pulled that little trick on you on homework, but just keep in mind in general, the data doesn't always have to be in the order that we're accustomed. So the point is, the temperature would be the X, and we use it to predict what the Y would be, how many emergency calls to expect. And so, if you make your scatter plot here very quickly, you'd have temperature of 68, 700 emergency calls. By the way, it did say in hundreds, I'm pretty sure. This is a large city. That's another thing. The emergency calls it said up here in the narrative was hundreds. And that'll come into play in the end. All right, let's see. When the temperature was 74, we had 400 emergency calls. So again, just get me in the ballpark here. I'm not going to get out a microscope and grade every little point here. 82 degrees, 800 emergency calls. 88 degrees, 100 emergency calls. That's 1,000 emergency calls. 93 degrees, 1,100 emergency calls. It seems to be so far that the general trend is that when the temperature goes up, the number of emergency calls also goes up. And we're not looking for reasons necessarily, we're just seeing if there's a relationship. 101, 1,300 emergency calls. Yeah, it seems like when the temperature goes up, when it gets hotter, cars break down more often. We're not looking for reasons, but that stands to reason to me a little bit. But this would seem to have an upward trend here. All right, and so it shouldn't surprise us. I would hope you would guess with me that if it is going to be a line, it's going to be in the positive direction, it seems. And therefore, the R value, I hope you would agree, would hopefully end up being somewhere in the positive 1 direction. That seems to be a positively sloped line. And by the way, this time we have how many data points? 1, 2, 3, 4, 5, 6, 7 data points. All right. Each line in that table would represent its own observation. This was one day, the temperature was 68. We had 700 emergency calls. This was another day. Okay? So, R value. This is very mechanical again. So to find that R value, and this is where we're going to go, do what we did before. And I've done this many times in my classes. This is where you would go through and make those columns for sigma xy, sigma x, sigma y, sigma x squared, sigma y squared, and you will find that in your materials. And just so we can refer to them by color, I believe you'll find that, sorry, there's so much to look at here, but you're going to find this in your materials. Let me just put up the slide here. Come on. All right, here it is. It's hard to see on the screen. You have it. It's in your PowerPoint slides. I made a column called XY, and you notice I put it in red. You went through and took each X times Y, wrote them all down, and then wrote the total down at the bottom, which you'll notice is 55, 35. And I'm just going to continually refer back to these columns. And then apparently, for whatever reason, I decided to call the x squared column, I did it in blue. And again, same thing, you go through and square each of these x's here. Now remember, this is x, right? That's important. And you'll notice that the sum of that column is up there on the screen as well as in front of you, 53,219. This is where you go through and square each individual x. All right, and then the green one, which admittedly is hard to read, but if you go through and square each individual y value, 7 squared, 4 squared, 8 squared, blah, 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 and add those up, I hope you can read the fact that that column adds up to 600. So, there's that table again, and you have it. It's in your materials. I'm not sure how legible it is. I think it came off pretty well if I look at the copy I have of it, and yours is in color. So, you know, red, blue, green colors, I think it all ought to be good. So in the interest of making space for the rest of this question, you start with your original data, you plot it, and then you use it along with that beautiful R formula to get your correlation coefficient. So again, we will continually refer back to that table as we pull this together. So please have that in front of you. I'm looking for my R value formula. Here it is. Okay. So here's the table. Here's the formula. Let's go for it. I have to erase this to make room. Keep that table in front of you. I think by now, and look, I've done it this way in lots of classes once we get to this. So I've had a lot of people go, yeah, I got it, I got it. Okay, and that would be the 7 data points, the 7 observations, the 7 lines in the table, sigma xy. All right, let's see, that would be that red column there, wouldn't it? I don't have these color coded. I hope that's right. Is that one red? Okay, thanks. 5535. Minus the sum of the x column. That'd be the 605, wouldn't it? And then times the sum of the y column. And that would be the 62. I hope I'm looking at the right table here. Emergency calls outdoor temperature. Yes. Square root, 2 brackets, bracket number 1, n, 7. All right, sigma x squared. That'd be that next to last column. I just want to make sure I refer to it by the proper color. I think it's blue, isn't it? All right, that's 53,219. Minus sigma x, that was the 605, squared, close the bracket. Second bracket, n, 7. The sum of the y squared column, that'd be that last column out there on the end. Was that in green, I believe? All right. And that was 600. Minus the sum of the y column. That's the 62. That was the very first column, and then squared and then bracket. And as mentioned before, it's highly recommended because we might be able to recycle some of these numbers later, but we're going to have 3 parts to this. And these are the parts you would crunch out individually when you do the order of operations anyway. So I would suggest to you, you got numerator, you got the first bracket, you got the second bracket, you crunch each one individually, and might I recommend again, you write them down. So, turns out that R would equal, and here's what I got when I did the math ahead of time. Hit pause, do it, I don't care. The numerator is 1235. The denominator would be square root, and then bracket number 1, I got 6508. And bracket number 2, 356. Crunch, crunch, crunch. I also want to remind you that you keep that to 3 decimal places. So there is, unlike a lot of our previous examples, there is guidance there. And I hope you got 0.811. 0.811. And you'll notice that's in the direction of positive 1. But again, the question that a statistician would have would be, okay, is that close enough to positive 1 to say they're linearly related? And so we'll hit pause now and make room for it, but you know the next thing that's going to happen. We're now going to take that R value and test it. do a hypothesis test of that R value to see if we can say there's a linear relationship between these two variables. So that's the next step in the process, and I think that's where we'll leave this one. So that's part one, to be continued.